Hey everybody, we are going to talk about recombinant DNA technology in this lecture. This lecture has been broken up into 5 parts. Now at the end of this lecture, you should all be able to describe recombinant DNA, list the uses for recombinant DNA technology. You should be able to identify the steps used for cloning and also to describe the theory of every step in cloning. Describe the use of restriction endonucleases in recombinant DNA technology. List examples of recombinant DNA technology. Describe gene therapy and discuss any concerns that recombinant DNA technology raises. Now, recombinant DNA technology. What is recombinant DNA technology? Well, recombinant DNA is when you combine the DNA from 2 different things. So, for example, if right here you had human DNA and here you had DNA from, let's say, a kiwi. That would be an example of recombinant DNA. You're recombining DNA from 2 sources. Now, the result of recombinant DNA would be recombinant protein. So your DNA, remember, you use your DNA to make messenger RNA. Your messenger RNA is translated into protein. So if your original DNA is recombinant DNA, what you would make after translation is a recombinant protein. So a protein that is made from DNA from 2 separate sources. Now, what the key for recombinant DNA technology is something called restriction endonucleases or restriction enzymes. And basically what restriction endonucleases are, they are molecular scissors. These are enzymes that will go in and cut DNA at very specific sequences. And without restriction endonucleases, we would not have recombinant DNA technology. So how do we use recombinant DNA technology? We use it in so many different ways. It can be used to generate hybrid plants, such as this example here with some hybrid strawberries. You get a blue strawberry here. You can use it to generate fluorescing bacteria like this right here. You can add a fluorescent marker into bacteria. It makes it easy to look for things. There's so many uses of recombinant technology, genetic engineering. A lot of our vaccines are made using recombinant DNA technology. So it is a huge and expanding field right now. And because of that, it brings in lots of money. It's a multi-billion-dollar industry. Now, we use recombinant DNA technology to do what's called cloning. And I'm sure everyone has heard of cloning. It's been in the news. Everyone's heard of the Dolly situation. So molecular cloning is when you take your recombinant DNA, your DNA from 2 different sources, you place that DNA into a vector, and there are various vectors that we're going to talk about in the next lecture. And from that vector, you place it into a quickly replicating organism in order to clone that recombinant DNA. So we'll talk about that further in the next several slides. Now, vectors, we mentioned vectors. There's many different types of vectors. Now, I'd have to say the most common vector is going to be the plasmid. That is definitely one of the more common vectors that are used. However, the bacteriophage, or phage as people call them, are also highly common. What differs in all of these vectors, we have cosmids, we have bacterial artificial chromosomes, we have YACs or yeast artificial chromosomes. How they differ is what host cell they're put in, and you can see most of them are put into E. coli, the bacterium Escherichia coli. The main difference is how much DNA can they hold. So if you're trying to put a big, huge chunk of DNA and clone that, you have to make sure you choose the right vector. So in kilobases, between 0.1 and 10 kilobases can fit inside of a plasma, or can be recombined into a plasmid, 10 to 20 kilobases in a bacteriophage, 35 to 45 in a cosmid, 80 to 100 in a specific bacteriophage, the P1 bacteriophage, 50 to 300 kilobases in a bacterial artificial chromosome, 100 to 2,000 in a yeast artificial chromosome. So how you design these, it depends on what the size of your insert. You're going to then choose the appropriate vector. But for most utilizations, the plasmid and the bacteriophage are used. So the common features of your cloning vectors, we're going to go over this pretty quickly. This is an example of a plasmid right here, and I said plasmids are very commonly used. Why are plasmids very commonly used? Well, plasmids have an origin of replication. You want to be able to replicate your recombinant DNA. So plasmids have this origin of replication, and you would pick the appropriate plasmid that has the origin of replication that you need. So if you were using E. coli as your cloning host, you would want the origin of replication for E. coli. Plasmids also have resistance genes, antibiotic resistance genes. This one is ampicillin resistance. Plasmids also have what's called a multiple cloning site. So in this multiple cloning site, there are sequences for specific restriction enzymes. And in this example, it's HinD3, PST1, EcoR1, SAL1, BAMH1, and KPN1. So the fact that plasmids have an origin of replication, a selectable marker such as an antibiotic resistance gene, and these cloning sites make them very good vectors for cloning.